Okay, so hello everyone. So after a long time, I'm making a video on my channel. So this will be about something called Grassmannian, which is a very important object, a well-known object in mathematics. And the story started with the German mathematician Hermann Grassmann. So he was a German polymath. Uh, so so he introduced the concept of Grassmannian, and so this is a well-known, interesting object in mathematics. I mean, this can be studied from different points of view. So I will try to explain those things. So first of all, let me define what is a Grassmannian. So suppose you start with a vector space, start with a vector space uh, over some field F. So this field is not necessarily finite. It could be an infinite field. It could be anything. Characteristic zero, characteristic positive, algebraically closed, non-closed. It can be anything. Just take a vector space over any field A, and let's say uh, let's call this vector space V, and let's say the dimension of this vector space is n. So I am fixing an integer, positive integer n. I am looking at n-dimensional vector space over the field F. Now, if I fix some positive integer a less than or equal to n, then this object Grassmannian, grk f to the n, this is defined as the set of all k-dimensional subspace of this vector space. Of this vector space V. So basically, what is my Grassmannian of degree k, let's say? So you take a vector space V. Suppose the dimension of the vector space is n, and then you look at all possible k-dimensional subspace of that vector space, and that collection is known as the Grassmannian. So that is a definition. So let's do a quick example. So suppose I say gr2 comma r3. Suppose I look at this Grassmannian. So R3 is my standard 3 space that we all live in. It's the most it is the most comfortable thing to visualize our usual day to day 3 space, and then I look at all possible 2-dimensional subspace of this R3. So basically, I will be looking at all possible planes that pass through the origin. So visually, I mean, you can visualize this at least in this example. Suppose this is my R3, and then you look at all possible 2-dimensional subspace. So geometrically, 2-dimensional subspaces are just the planes passing through the origin. So suppose this is a plane that passes through origin. My picture is very bad, but anyways, you know what I'm trying to say. Uh, so this collection, this set of all the set of all planes that pass through the origin, that is a Grassmannian of degree 2 in the vector space R3. So if I say instead of GR2 R3, if I say GR1 R2, so you know what is this. So this is my plane R2, and then I'll be looking at all possible one-dimensional subspace of the vector space, and geometrically they are nothing but lines passing through the origin. So you will be looking at all possible lines, that pass through the origin. Of course, this is an infinite set. And this collection is known as the Grassmannian of degree 1 inside the vector space R2. So now, why this kind of spaces are important? I mean, you might wonder why we are defining such an object. So yeah, you will see if you stay till the end of the video, then you will see that why it is important. So as I said in the beginning, the field can be anything. I mean, it can also be a finite field, and that is what combinatorialists are interested in. So if you are interested in combinatory, let me just change the color. Yeah. So yeah, if you are interested in combinatory, then you want to study Grassmannian uh, over the finite fields. So if you are someone who is interested in discrete mathematics, if you are interested in counting or enumeration, and discrete structures like graphs or some permutation combination problem, if those kind of things interest you, then uh, this is a very interesting thing to look at. So suppose I talk about um, a finite field f. So I will denote the finite field by fq. So by fq, I mean finite field of order q, cardinality q. So now if I take some uh, yeah, so if I want to look at all possible k-dimensional subspace of the vector space fq to the n, then if you do combinatorics, then you are interested in the cardinality of the set. So fq is a finite field, and then this vector space fq to the power n is also a finite set, and then you are looking at all possible k-dimensional subspace of that n-dimensional vector space over fq. That is also a finite set, and you are interested in counting the number of elements of this set. So what is the cardinality of grk f2n? So that is one interesting question to begin with. So let's do this. So actually, this is a very common question. I mean, I have uh, I have seen this question appearing in many exams, in many interviews over the years, and many people solve this. I mean, different people solve this problem in different ways. Uh, but I will show you how to use group action to count the number of elements of this set. I think that is one of the smartest way to do this, at least in my opinion. So let's see how to do this. But for that, I will just recall some basic things. So let's say you have a finite group G that is acting on some set X transitively. Transitively, this action is happening. Then, if you want to count the cardinality of X, that is just order of G by order of the stabilizer of some point, right? So this is basic orbit stabilizer theorem. You can try to prove it. This is a very basic exercise in the theory of group actions, that the group G, a finite group G acts on a finite set X transitively. Then what is the cardinality of the set X? That is just the order of G divided by the order of the stabilizer of X. And this X is some particular point in X. You can choose this X to be any point. So fix a point small x in the space capital X, look at the stabilizer, count the number of elements, then order of G divided by that number is the cardinality of the set X. That is basic orbit stabilizer theorem. So you can use this to count the number of elements in the set. For example, it's Grassmannian, GRK FQ to the N. Okay, so how can you do it? So one thing is clear, that somehow we have to cook up a group that is acting on this space. So can you think of such a group, I mean, which is acting on this collection, a set of all k-dimensional subspace of the vector space Fq to the N? And that is very easy. That group is just GL of Fqn, isn't it? So what is GL of Fq to the N? This is just set of all invertible linear transformations of the vector space Fq to the N. And this group naturally acts on set of all k-dimensional subspace of Fq to the N. So how does it act? The action is very clear. So if you choose a k-dimensional subspace, so let's choose an element of this set GRK Fq to the N, and then choose the invertible linear transformation A of the vector space Fq to the N. Then how does it act? How does A act on Y? This is just natural action. So A is a linear operator, Y is a k-dimensional subspace. So I can just look at the image. I can just look at the image of Y under the linear operator A. So any linear transformation, invertible linear transformation, will take a k-dimensional subspace to another k-dimensional subspace, and this action is transitive. This is a basic exercise in linear algebra, that if you take any two k-dimensional subspace, then you can find an invertible linear transformation which takes one k-dimensional subspace to another. So basically this group GLFQN acts on the set GRK Fq to the N transitively. So now all we have to do is to count the order of the stabilizer. Now there is a very natural trick to count the order of this group GLFQN and the order of the stabilizer. So how to do that? Okay, so the main idea is that you have to think in the matrix form. So if we choose a basis so of the vector space V, so let's say, so I mean we are only discussing about fq to the power n. So let's say my vector space V is fq to the n, and then if I fix a basis of this V, then this GL FQN can be identified with set of all invertible matrix, right? So this is GL N FQ. So this is set of all n by n invertible matrix over the field. So if I choose a basis of the vector space, then I can write any invertible linear transformation in a matrix form. Then I can identify GLFQN with simply the set of all n by n invertible matrix over the field F, that is GLNF notation. So this is transitively acting on set of all k-dimensional subspace of the vector space FQ to the n. Now, what kind of basis is convenient to choose for this problem? That you have to think about. That is something you have to think about. And one natural choice is that, so since we are interested in counting the cardinality of the stabilizer of a particular point in the set GRK FQN, so I can just fix a k-dimensional subspace. So this is a k-plane. By k-plane, I just mean k-dimensional subspace in my vector space FQ to the n, and then I can choose a basis for this k-dimensional subspace. I can choose a basis for this space, and and then I can extend that basis to a basis of the whole vector space. So let me repeat what I am doing. I'm choosing a basis of the. I am first of all I am fixing a k-dimensional subspace. I'm choosing a basis for that k-dimensional subspace, and then I am extending that basis to a basis of the whole vector space. So I am fixing that basis. So let's call that basis B. So I am fixing this basis. Now with respect to that basis, I will write down the matrix of any invertible linear transform. So now how does this matrix looks like if that matrix fixes that k-dimensional subspace? So if you just pause and think for a moment, very easily you can see that uh, the matrix will be of this form, of the following form. This will be a n by n invertible matrix, and then since I am choosing a so basically whenever I say basis, I will always mean a ordered basis. So how have I chosen the ordered basis? I have chosen a basis for the k plane, then I have extended to a basis of the whole vector space. Now if a matrix fixes this k dimensional subspace, then how should this matrix should look like? This should look like the following. So you will have a k cross k block here, right? You will have a k cross k block here, because I mean this linear operator fixes this k dimensional subspace. So I have a k cross k block here, all the zeros down there, and then I can choose anything in other in the rest of the columns. In the remaining columns, I can choose anything. So I mean, these entries can be anything. I can choose them in any way possible. So this will look like this. So on the top left corner, you have a k cross k block, and below that block, you have some zeros. And in the remaining columns, I can choose anything. But remember, this is an invertible matrix. So, so this block also has to be inverted. And what is the order of this block? This is basically n minus k cross n minus k block, right? And this block itself is invertible because the whole matrix is invertible. So I'm looking at invertible uh, matrices only over the field FQ. So I mean, this is a block upper triangular kind of matrix. So if it is invertible, then both of these blocks should be invertible. So so basically, I have to choose a k cross k invertible matrix in this block, and then I have to choose n minus k cross n minus k invertible matrix in this block, and in this portion I can choose anything. In this portion I can choose anything. So this is the order of the stabilizer. So you have to count the number of all possible matrices with a k cross k invertible block in the top left corner, and then n minus k cross n minus k invertible block, and in this position you can choose anything. So then what will be the order of the Grassmannian? So the order of the Grassmannian GRK FQ to the n, that is just order of GLN FQ divided by, I mean, order of this set, whatever I have explained. So now I think you know what is the order of GLN FQ. What is the order of GLN FQ? So this is a very famous formula. In, also, you can do this as an exercise, a very simple exercise. Order of GLN Q is just so what is the order? Order is q to the power n minus 1 into q to the power n minus q, q to the power n minus q square, and so on. Then q to the power n minus q to the power n minus 1. That is the formula. So this is the order of the GLN. And then similarly, you can easily count the order of the stabilizer. So what will be that? So you have to count the number of k by k invertible matrix over FQ. Then you have to count the number of n by k cross n minus k cross n minus k invertible matrix over FQ. both of which you can do using the formula that I have discussed already. And then in this upper right corner, I mean, you can choose whatever you want. So you can count that. So just take this as an exercise and just write down the explicit formula in the comment section. Just take this as an exercise. You just do it on your own. I mean, you just write down the exact closed form expression. I think it's a nice exercise. So this is the part that is what is interesting to combinatorialist. So as we have seen, this is basically a counting problem. So I have a finite set and I have some finite collection, that is the all possible k-dimensional subspace of some finite vector space. And then this is just a counting problem. This is just a nice problem in combinatorics. And this is not, I mean, you do not need any extraordinary machinery to solve the problem. This is all just basic linear algebra. But you just have to be careful how to fix a basis and how to write down the matrix in the suitable form, and then knowing some basic things. For example, this formula that I have discussed. You can also do this as an exercise. Why order of GL and FQ is this? And then the rest of the things that we need. Now I want to discuss some interesting thing. So maybe in the next video I will talk about this thing, the Grassmannian as a smooth manifold. Is Grassmannian as a smooth manifold. Then Grassmannian as a algebraic variety. And Grassmannian as a homogeneous space. So, this object is this object appears in many places, but then we have to go to infinite field. For example, real number, complex number, and then if you look at Grassmannians over complex numbers or real numbers, then these objects are very nice objects. I mean, sometimes these are smooth manifold. Sometimes this can be viewed as a homogeneous space. I will explain all these terms. Sometimes there's some nice algebraic varieties and so on. So maybe there will be a part two of this video. In part two, I will discuss about those things.